We finished the discussion on the mechanics of systems of point masses with the virial theorem proven for such systems. In order to introduce the quantity called virial playing the basic role in this theorem, we need to generalize the concept of moment of inertia of a system of point masses about an axis to the moment of inertia about a point. Let us consider a system of point masses m1, m2, ellipsis, mn, and denote the position vector of the point mass mi with respect to a reference point O by Ri from I equals 1 to n. Let also Vi denote the velocity of the point mass mi, where the momentum pi of the point mass is given by the product of its mass mi and its velocity Vi. The net force Fi acting on the point mass mi is equal to the vector sum of all the forces exerted on the point mass. For such a mechanical system we can define the moment of inertia I about the point O by the sum of the product of the mass mi and the square of the magnitude of the position vector Ri from I equals 1 to n. Here the square of the magnitude of the position vector Ri is simply given by the dot product of the vector with itself. We note that the definition of I can be expressed as a function of the distances between the point masses of the system. If we determine the sum of the mass mi times the mass mj times the dot product of the difference between the position vectors Ri and Rj from I and j equal 1 to n. Because the dot product can be written as Ri squared minus 2 times the dot product of Ri and Rj plus Rj squared, we can express the right-hand side as three terms containing double sums. The first term is given by the sum of mj from j equals 1 to n, times the sum of mi times Ri squared from I equals 1 to n, whereas the second term is equal to minus 2 times the dot product of two sums. The sum of mi times Ri squared from I equals 1 to n, and the sum of mj times Rj squared from j equals 1 to n. The last term is given by the sum of mi from I equals 1 to n, times the sum of mj times Rj squared from j equals t to n. Both the sums of the masses mi and mj in the first and the last terms give the total mass m of the system, whereas both the sums of the products of mi and Ri squared and the products of mj and Rj squared are equal to the moment of inertia I of the system. Then we have 2 times the total mass m of the system times its moment of inertia I. In the dot product in the second term can recognize the mass m times the center of mass or c of the system, that is we have minus 2 times m squared times or c squared. Since the left-hand side is symmetric the indices I and j, we can express the moment of inertia I from this equation as 1 over the total mass m times the sum of the mass mi times the mass mj times the square of the distance r sub ij between the point masses mi and mj from I equal 1 to n and j less than I, plus the total mass m times the square of the center of mass or c. This form of the moment of inertia is more useful for the study of the time evolution of the distances between the point masses in a system. Now we use the original form of the definition of the moment of inertia to calculate the rate of its change. For the sake of convenience we determine 1 over 2 times the derivative of I with respect to the time t. Then we obtain the sum of mi times the dot product of the time derivative of Ri and Ri from I equals 1 to n. Here Ri dot is simply the velocity Vi of the point mass mi, and mi times Vi is defined as the momentum pi of the point mass. As a result, the second-order derivative of the moment of inertia I with respect to the time t can be written as the sum of the dot product of the derivative of the momentum pi and the position vector Ri from I equals 1 to n, plus the sum of the dot product of pi and the derivative of Ri. The derivative of Ri in the second term can also be written as Vi. For the first term in the right-hand side we can apply the equations of motion of the system stating that the time derivative of the momentum pi of the point mass mi is equal to the net force Fi acting on the point mass where the index I is running from 1 to n. If we insert these equations into the second-order time derivative of the moment of inertia I, then the first sum becomes the dot product of the force Fi and the position vector Ri, whereas the second sum can be written as the mass mi times the dot product of the velocity Vi with itself. In the second sum the dot product gives the square of the velocity Vi, where we can identify the total kinetic energy of the system defined as the sum of the kinetic energies of the individual point masses, that is 1 over 2 times the sum of the mass mi times the square of the velocity Vi from I equals 1 to n. Now we substitute the definition of the total kinetic energy of the system into the equation describing half the second-order time derivative of the moment of inertia, which we can also call the acceleration of the inertia I, and write it as the sum of the dot product of the force Fi acting on the point mass mi and the position vector Ri of the point mass from I equals 1 to n, plus 2 times the total kinetic energy of the system. In the 19th century when Rudolf Clausius, a German theoretical physicist, formulated and proved the Virial Theorem, it was a common practice to assign a Latin name to any special characteristic of a physical system. At that time kinetic energy was often called vis viva, meaning living force, and Clausius also coined the term virial stemming from the plural form virias of the word vis, that is force. He called half the first term in the right-hand side virial, that is the half the sum of the dot product of the force Fi and the position vector Ri from I equals 1 to n represented a special property of the system of point masses for Clausius. This quantity summing up the projections of the forces acting on the point masses onto the position vectors of the point masses measures the bound due to the interactions between the particle, where the forces include the forces of interactions. Then the equation in the left-hand side states that half the acceleration of the moment of inertia of a system of point masses is given by the sum of 2 times the virial representing the forces acting on the system and 2 times the kinetic energy of the system. If all the forces Fi acting on the point masses Mi are conservative forces, that is the system of point masses is a conservative system, then we can define the potential energy of the system as a function of the position vectors Ri of the point masses for the index I running from 1 to n. Each conservative force Fi acting on a point mass Mi is given by the negative gradient of the potential energy of the system, where the gradients are always calculated with respect to the components of the position vector Ri of the point mass. For example, if we attach the origin of a Cartesian coordinate system to the reference point O, then the Cartesian coordinates of the position vector Ri can be written as xi, yi and zi. Similarly, the Cartesian components of the force Fi denoted by f sub ix, f sub iy, and f sub iz are equal to the negative partial derivative of the potential energy with respect to the corresponding coordinate of the position vector Ri. Then the sum in the virial can be written as the sum of f sub ix times xi, plus f sub iy times yi, plus f sub iz times zi from I equals 1 to n, or minus the sum of 3 terms, xi times the partial derivative of the potential energy with respect to xi, plus yi times the partial derivative of the potential energy with respect to yi, plus zi times the partial derivative of the potential energy with respect to zi, from I equals 1 to n. Because the terms in the parentheses give the projection of the gradients into the direction of the position vectors of the point masses, half the virial is equal to the sum of the directional derivatives of the potential energy of the system along the position vectors for all particles in the system. As a result, 1 over 2 times the second-order time derivative of the moment of inertia I of a system of point masses under the influence of conservative forces is given by 2 times the total kinetic energy of the system, minus the sum of the directional derivatives of the potential energy of the system along the position vectors Ri from I equals 1 to n. In many cases the potential energy of a mechanical system under the influence of conservative forces is a homogeneous function in its variables, normally some coordinates describing the configuration of the system. Then Euler's theorem for homogeneous functions can be applied in calculating the gradient of the homogeneous potential energy of the system, which allows us to simplify the virial in the second-order differential equation of the moment of inertia of the conservative system. We call a function f of n variables a homogeneous function of degree k in its first variables x1, x2, ellipsis, xm with m less than or equal to n, if the function f evaluated at lambda times x1, ellipsis, lambda times xm, xm plus 1, ellipsis, xn, is equal to lambda to k times the function f evaluated at x1, ellipsis, xm, xm plus 1, ellipsis, xn. Here lambda is an arbitrary real parameter. First we compute the derivative of this equation with respect to the parameter lambda. By introducing the notation y for lambda times xi, we can write the derivative of the left-hand side as the derivative of the function f evaluated at y1, ellipsis, ym, xm plus 1, ellipsis, xn with respect to lambda, and apply the chain rule for the function yi. Then we obtain the sum of the partial derivative of the function f with respect to yi at constant yj where j is not equal to I, times the partial derivative of yi with respect to lambda, from I equals to 1 to m. If we substitute the definition of yi into the derivatives, then we take the partial derivatives of the function f with respect to lambda times xi, and the derivative of yi with respect to lambda can be written as xi. Now we compute the derivative of the left-hand side of the definition of the homogeneous function f. The derivative of lambda to k times the function f with respect to lambda, is equal to k times lambda to k minus 1, times the function f. By inserting these two equations into the derivative of the definition of the homogeneous function f and setting the arbitrary parameter lambda to 1, we obtain Euler's theorem for homogeneous functions, which states the following. If a function f of n variables is a homogeneous function of degree k in its first m variables, then k times the function f is equal to the sum of the derivative of the function f with respect to xi, times xi from I equals to 1 to m. If we suppose that the potential energy of a conservative system depends on n position vectors and it is a homogeneous function of degree k and its all variables, then we can state that the potential energy of the system evaluated at the position vectors are I scaled by the factor lambda, is equal to lambda to k times the potential energy evaluated at the positions are I from I equals 1 to n. By applying Euler's theorem for such a homogeneous potential energy, we can write the sum of its directional derivative along the position vectors from I equals 1 to n, as k times the potential energy itself. As a result, the half the acceleration of the moment of inertia I of a conservative system with a homogeneous potential energy of degree k can be written as 2 times the kinetic energy of the system, minus k times the potential energy of the system. Now we will provide an example of a mechanical system that has a homogeneous potential energy as an illustration of Euler's theorem applied in the calculation of the virial. Let us suppose that a system of point masses is a closed system, that is, no external forces are applied on the particles in the system. Then the net forces acting on the point masses are the internal forces describing the interactions between the particles, and the force Fi acting on the point mass mi is the vector sum of the forces F sub ij exerted on the point mass mi by the point mass mj for I and j equal 1 to n, where the indices I and j are different. The later condition indicates that there is no self-interaction in particles, and the vector sum of these forces gives the net effect on the point mass mi by the rest of the point masses in the system. By substituting this vector sum into the force Fi in the virial of the system of point masses, we can write its sum as the sum of the dot product of the force F sub ij and the position vector Ri from I and j equal 1 to n, where I is not equal to j. Now we expand the double sum as follows. In the first row we write the terms with the index I equals 1 while expanding the sum with the index j. Because the index I must not be equal to the index j, we start with a vanishing term for I equals j where the force F sub 1 is equal to 0. Then we have F sub 1 2 times R1, plus F sub 1 3 times R1, plus ellipsis, plus F sub 1 n times R1. In the second row we write the terms with the index I equals 2, which are plus F sub 2 1 times R2, plus a vanishing term, plus F sub 2 3 times R2, plus ellipsis, plus F sub 2 n times R2. In the third row we can write the next terms, plus F sub 3 1 times R3, plus F sub 3 2 times R3, plus a vanishing term, plus ellipsis, plus F sub 3 n times R3. We can follow the same pattern till we reach the last row for I equals n, which has the terms plus F sub n 1 times Rn, plus F sub n 2 times Rn, plus ellipsis, plus F sub n minus 1 times Rn, plus a vanishing term. Then we have n terms including one vanishing term in each row and all the terms are ordered in n rows. Because the terms of the sum are arranged in an n times n block, we have a matrix pattern where zeros can be found in the diagonal positions separating the areas of the lower and upper diagonals. Here we have collected the terms from the lower and upper diagonal positions of this sum separately into two groups arranged in two rows by applying the following strategy. We started with the first term in the second row belonging to the lower diagonal area, that is F sub 2 1 times R2 denoted by the yellow rectangles. Then we collected the terms in the third row belonging to the lower diagonal area into one sum denoted by the orange rectangle. We followed the same procedure till the last row where we collected the terms belonging to the lower diagonal area into one sum denoted by the red rectangle. We collected the terms in the upper diagonal area in a similar way. We started with the second term in the first row belonging to the upper diagonal area, that is F sub 1 2 times R1 denoted by the green rectangles. Then we collected the third column of the terms belonging to the upper diagonal into one sum denoted by the blue rectangle. We followed the same procedure till the last column of terms where we collected the dot products into one sum denoted by the purple rectangle. By collecting the terms from the lower and the upper diagonal areas and the sum of the virial we have obtained a set of sums arranged in two rows, which can be combined into two double sums. Then the sum in the virial of the system of point masses is given by the sum of the dot product of the force F sub ij and the position vector Ri from I equals 1 to n and for j less than I, plus the sum of the dot product of the force F sub ji and the position vector Rj from I equals 1 to n with the indices j greater than I. Here we can apply the third law of motion stating that the action F sub ij is equal and opposite to the reaction F sub ji for all the indices I and j running from 1 to n. If we substitute this law into the second sum in the right-hand side, then the sum in the virial of a system of point masses free from external forces reduces to the sum of the dot product of the force F sub ij and the difference between the position vectors Ri and Rj from I equals 1 to n and for j less than I. Because the difference between the position vectors of the point masses mi and mj gives the vector pointing from the point mass mj to the point mass mi, the dot products in the sum can be interpreted as the work done by the force Fij on the point mass mi over the distance connecting the two point masses. This means that the virial of a closed system of point masses is determined by the sum of the works done by the forces of interaction between the particles over the distances between them. After having expressed the virial of a closed system in terms of the interaction forces, we will assume that these forces are conservative, that is, they are independent of the velocities of the point masses and do not have explicit time dependence. In that case, we can define the total potential energy of the system of point masses as the sum of the potential energies of all the point masses in the system due to the interactions between the particles. Normally, the potential energy of the interaction between the point masses mi and mj only depends on the distance between the point masses, that is, the magnitude of the difference between the position vectors Ri and Rj. The force F sub ij describing the interaction between the point masses mi and mj is then given by the negative gradient of the interaction potential energy between the two particles with respect to the position vector Ri of the first point mass. Both of these relations will be applied when we determine the sum of the virial of a closed conservative system, which is expressed as the sum of the dot product of the interaction force F sub ij and the difference between the position vectors Ri and Rj from I equals 1 to j and for j less than I. First, we insert the negative gradient of the potential energy of the interaction between two particles, and use the chain rule by writing the gradient of the potential energy depending only on the distance R sub ij as its derivative with respect to R sub ij, times the difference between Ri and Rj over R sub ij. Here we obtain the dot product of the difference between Ri and Rj, which gives the square of its magnitude. Because the later is just the square of the distance R sub ij between the point masses mi and mj, the sum in the virial can be written as minus the sum of the derivative of the potential energy of the interaction between the point masses mi and mj with respect to the distance R sub ij, times the distance R sub ij from I equals 1 to n and for j less than I. The potential energy of the interaction between the point masses mi and mj normally obeys some power law of the distance between the particles, that can be written some real constant alpha sub ij, times the distance R sub ij between the point masses to the power of k, where k is an integer. If the interaction between the system of point masses is described by Newton's law of gravitation, then the magnitude of the force F sub ij exerted on the point mass mi at the point Ri by the point mass mj at the point Rj, is given by minus the gravitational constant times the product of the masses mi and mj over the square of the distance R sub ij between the point masses. Its direction is determined by minus the unit vector Ri minus Rj over its length, which points from the point mass mi to the mj. Because gravitational forces are conservative, the potential energy of the gravitational interaction between the 2 point masses can be defined, and it must be equal to minus the gravitational constant g, times the product of the masses mi and mj over the distance between the point masses given by the magnitude of the difference between the position vectors Ri and Rj. Then the multiplication factor in the power law for gravity is given by minus g times mi times mj, and the exponent k is equal to minus 1. The derivative of the potential energy of any interaction between 2 point masses mi and mj described by the power law with respect to the distance Rij between the point masses, is equal to k times alpha sub ij times R sub ij to k minus 1. If we substitute this result into the sum of the virial in the left-hand side, then we obtain minus k times the sum of alpha sub ij, times the distance R sub ij to k from I equals 1 to n and for j less than I, which is equal to minus k times the sum of the potential energies of the interactions between the point masses mi and mj from I equals 1 to n and for j less than I. Since the double sum gives the total potential energy of the interactions between all the point masses in the system, we conclude that the sum in the virial is equal to minus k times the potential energy of the system. This is an illustration of the fact that the potential energy of a conservative system with a power law interaction potential is a homogeneous function of degree k. Indeed, any scaling of the distance R sub ij in the power law by lambda can be factored out, producing a multiplication factor of lambda to k. We have already established that 1 over 2 times the second-order time derivative or the acceleration of the moment of inertia I of a conservative mechanical system where the potential energy is a homogeneous function of degree k in its variables, that is the coordinates describing the state of the system, is equal to 2 times the kinetic energy of the system, minus k times the potential energy of the system. As seen in the example of Newton's law of gravitation, the degree k is equal to minus 1 for a self-gravitating system of point masses, which gives Lagrange's identity stating that 1 over 2 times the second-order time derivative of the moment of inertia I, is equal to 2 times the kinetic energy of the system plus the potential energy of the system. This identity was introduced in the study on the three-body problem in 1772 by Joseph Louis Lagrange, an Italian-French mathematician and physicist, although he did not use the modern terminology of moment of inertia or energy. Besides Lagrange's identity, the law of conservation of energy also holds for a closed system, stating that the total energy E of the system given by the sum of its kinetic energy and its potential energy is constant. Then we can write that the constant total energy E minus the potential energy of the system is equal to its kinetic energy, which is always greater than or equal to zero for a system of point masses due to the fact that its kinematic energy is a quadratic function of the velocities of the particles. The kinetic energy of the system only vanishes if all the point masses in the system stay at rest. If we insert this equation into Lagrange's identity, then we obtain the Lagrange-Jacobi formula, stating that 1 over 2 times the second-order time derivative of the moment of inertia I is equal to 2 times the total energy of the system minus the potential energy of the system. This formula was derived by Carl Gustav Jacob Jacobi, a German mathematician who generalized Lagrange's identity to the n-body problem. We have already seen that the potential energy for the gravitational interaction between particles is negative. It therefore follows from the law of conservation of energy that the total energy E of a self-gravitating system must be positive. As a result, the right-hand side of the Lagrange-Jacobi formula is positive, that is, the second-order time derivative of the moment of inertia I is positive. In other words, the rate of change of the moment of inertia is increasing, and it has a consequence related to the stability of the self-gravitating system. The Lagrange-Jacobi formula is a second-order differential equation with respect to the time, and we need to integrate it 2 times to solve it for the moment of inertia I. The first integration gives an equation stating that 1 over 2 times the derivative of the moment of inertia I is equal to the integral of the difference between 2 times the total energy E and the potential energy from 0 to the parameter t0 with respect to the variable t1, plus an integration constant denoted by I1. The second integration gives 1 over 2 times the moment of inertia I as a function of time expressed as the double integral of the difference between 2 times the total energy E and the potential energy, from 0 to t0 and from 0 to t with respect to t1 and t0, plus the integration constant I1 times the time t plus a second integration constant I0. Because the total energy E is constant for a closed system, it can be integrated 2 times, and 1 over 2 times the moment of inertia I can be expressed as the total energy E times the square of the time t, plus the integration constant I1 times the time t, plus the integration constant I0, minus the double integral of the potential energy of the system with respect to the time. We saw that the total energy is positive and the potential energy is negative in the case of a closed self-gravitating system of point masses. It can also be shown that the potential energy is bounded for such a system, and its double integral can be replaced by a constant representing the negative lower bound times the square of the time t. Then the moment of inertia I is the order of the square of the time t as the time t tends to infinity, that is, the moment of inertia diverges with time. We can understand the consequence of its divergence if we look at the moment of inertia of a system of point masses expressed in terms of the distances between the particles in the system. We found that it is 1 over the total mass m of the system, times the sum of the mass mi times the mass mj times the square of the distance r sub ij between the particles from I equals 1 to n and for j less than I, plus the total mass m times the square of the center of mass or c of the system. When studying the law of conservation of momentum, we also saw that the center of mass of a closed mechanical system either performs a uniform motion in a straight line or remain at rest. If we attach the frame of reference to the center of mass by choosing RC as the reference point O, then the second term in the right-hand side vanishes and the moment of inertia only depends on the instantaneous distances between the particles of given masses. If the moment of inertia for such a system diverges, this formula shows that at least one of point masses moves away from the rest of the particles and travels to infinity. After the introduction of the Lagrange-Jacobi formula, Jacobi developed the stability criterion for n-body systems based on this result in his lectures on dynamics delivered in 1842. His theorem states that if the total energy of a conservative system is positive, then at least one of the mutual distances between the point masses will increase to infinity as the time tends to infinity. In general, this theorem on the stability of the systems of gravitating bodies with non-negative energy states that some of the inter-particle distances either become indefinitely small or grow to infinity, that is, the system of point masses is unstable and it must disintegrate. The integration of the Lagrange-Jacobi formula with respect to the time shows that the integrating or averaging of the moment of inertia over an interval of time can also be applied in the proof of the Virial theorem for mechanical systems. In order to perform the averaging of a physical quantity f over a long or even an infinite interval of time, that is, determine the mean of f as a function of time t over a period of time tau, we define its time average by 1 over tau times the integral of the quantity f from 0 to tau with respect to the time t, where tau tends to infinity. By applying the Newton-Leibniz rule, the mean of the function f over the period of time tau can be written as 1 over tau, times the difference between the function F evaluated at tau and 0, as tau tends to infinity. Here F is the primitive function of the function f. Then the average of the quantity f is determined by the behavior of the primitive function at the limits of the time integration. If the difference in the brackets is bounded, then the limit in the averaging is equal to 0. If the difference diverges on the order of the time t to k as tau tends to infinity, then the exponent k will determine the result of the averaging. If k is less than or equal to 1, then 1 over tau times the difference is bounded, otherwise the average of f over an infinite period of time is divergent. We will show some examples of the function f of time which can be averaged over an infinite interval of time. For a periodic function, for example a times the sine of b times t with the graph in red, the limit of the integral divided by the period of time tau vanishes. One can interpret this result as the integration can be performed over an integer number times the period of the function f, which always gives 0 even if the integer number tends to infinity. We can also consider a times the exponential function with the negative exponent minus b times t plotted in green, which has a convergent integral between 0 and infinity. As a result, its average vanishes as well. However, if its exponent is positive as seen in the yellow graph, then the integral of the unbounded function growing faster than tau gives a divergent average. This is the case for linear functions like a times t plus b plotted in blue as well, since its integral is the order of tau squared. The function a times the natural logarithm of b times t seen in magenta graph has a similar behavior as its integral grows faster than tau. If we average Lagrange's identity over time, then we need to evaluate the average of the second-order derivative of the moment of inertia I with respect to the time t in the left-hand side of the identity. When integrating the left-hand side with respect to the time t, we apply the Newton-Leibniz rule and subtract the primitive function of the second-order time derivative of I, that is its first-order time derivative evaluated at tau from the derivative of I evaluated at 0, where tau tends to infinity. For a system of point masses performing a periodic motion, it is enough to integrate the acceleration of the moment of inertia over the period of the motion of its particles. Then we obtain the same values for the derivative of I at the beginning and the end of the period, and their difference vanishes. If a non-periodic system is bounded and its particles go in regular orbits, the moment of inertia of the system will oscillate regularly between two finite values. Then the derivatives of the moment of inertia evaluated at the initial time 0 and at any tau are finite as well, and their difference is bounded. Since it is divided by tau, it vanishes as tau tends to infinity. As a result, the time average of the left-hand side of Lagrange's identity is equal to 0 for a periodic or any bounded system. The vanishing time average of the second-order time derivative of the moment of inertia of a self-gravitating system describes some kind of quasi-steady state in which the system is in a dynamical equilibrium. We can formulate the result of the averaging of Lagrange's identity in the Virial Theorem proved by Clausius in 1870, stating the time averages of the kinetic and potential energy of a stable conservative mechanical system are related by the following formula. Twice the average of the kinetic energy over a period of time is equal to minus the average of the potential energy over the same period of time, or the time average of the kinetic energy is given by minus half the time average of the potential energy. The period of time must be long enough so that the averaging could provide the mean kinetic and potential energy of the system. The Virial Theorem is a fundamental relation between the kinetic and potential energy of a mechanical system, and it is valid for a wide range of natural phenomena that is governed by the action of different physical interactions between the constituent particles of the system. For stable non-conservative mechanical systems where no potential energy can be defined, the Virial Theorem still holds, stating that its averaged kinetic energy of the system over time is given by minus the average of the virial of the system over time. Or as Clausius stated, the mean vis viva of the system is equal to its virial. This form is very important in the kinetic theory of gases, where the gas is not considered as a continuous medium but a many-particle system formed by the atoms or molecules of the gas. In other words, both the forms of the theorem tell that if a stable mechanical system reaches a quasi-static state where it is in a dynamic equilibrium, then its average kinetic energy is equal to minus the average of its virial or potential energy. Such a process whereby a self-gravitating system attains stability is called virialization, and the system is said to be virialized. If we do not restrict our attention to gravitational interaction and study the general case of stable conservative systems with potential energy that is a homogeneous function of degree k, then the Virial Theorem states that twice its averaged kinetic energy over a period of time, minus k times its averaged potential energy over the same period of time vanishes. For closed systems the law of conservation of energy always holds, therefore the sum of the time average of the kinetic energy and the time average of the potential energy is equal to the total energy of the system, which is constant.